Let's look at the speed of a wave in general, and then we're going to look at the speed of sound in particular. First, let's review the types of waves that we are familiar with. So the types of waves are transverse and longitudinal. And I have here a class demo I like to use. It's a very old machine, and you'll hear how squeaky it is, but that's part of the charm of this thing. So in the back of this box, there is a handle that you can crank, and this is what happens when we do that. So you can follow either one of three waves. The top one is a water wave, and we don't care about that at this point. Then the second one is a sound wave, and the third one is what back when this box was created was called an ether wave. So let's follow this ether wave first. You see that the particles just basically move up and down as the wave seems to be oscillating to the right. Then looking at the sound wave, we see that these particles move back and forth in the direction of motion of the wave itself. So the bottom wave, the ether wave, since the particles move perpendicular to the direction of motion of the wave, it's called a transverse wave. The second one here, the middle one, for the sound wave, the particles move back and forth along the direction of propagation of the wave, and that's called a longitudinal wave. Now, a water wave is a combination of both, so let's look at that. See how these particles basically circle instead of just moving left and right or up and down. Now, for both water waves and sound waves to propagate, they need to be in a medium. The ether waves, which we now know that they are electromagnetic waves, they do not need a medium through which to propagate. They can propagate just as well in vacuum, thankfully, because that's how we get our light from the sun. Now, I have here a plain old wave, and it looks like a transverse wave. It looks like the ether wave that we saw before. But in this situation, this wave that I'm drawing here is to illustrate wave on a string. So we give this wave a little impulse here. We move it up or down, and the wave is going to propagate. Now, since it is along a, let's say, an elastic band, then each of these particles is going to influence the motion of the particle next to it. So we don't really have an ether wave like we have here, a transverse wave like we have here, where the particles never touch one another, but we have the particles influencing one another along the motion of the wave as well. So we have to take into account those tension forces between them to determine the speed of the wave. So here we have the equation for the speed of a wave on a string. This is that tension force, or the force between the adjacent particles, and m over L is what we call the linear density of the string. M is the mass, L is the length of the string. So the speed of a wave on a string doesn't just depend on particles moving up and down like we know with a transverse wave, like an electromagnetic wave, but there is an influence from the forces between adjacent particles, and this is how that wave propagates. Now let's look at a mathematical description of a wave, and we will incorporate some of this velocity business in it. Here we have two equations, and the two of them differ by a single sign. This one has a negative sign, this one has a positive sign, and that's because the top wave equation is for a wave traveling in the positive x direction, whereas the bottom one that has a plus travels in the negative x direction. Now, what are the different things that we have in here? So A is the amplitude of the wave. Omega is something we know already. It's the angular frequency, and it's equal to 2 pi divided by the period. So we have amplitude, which is the maximum displacement from equilibrium, omega, the angular frequency, and t being the period. Remember that 1 over period is also frequency, so we can write this as omega equals 2 pi times f. Now k is to lambda what omega is to t. So k, called the wave number, is 2 pi divided by the wavelength of the wave. So then this entire thing here, omega t minus kx, can be rewritten as 2 pi over period, 2 pi over period times time, minus 2 pi over wavelength times x. And it is called the phase angle. Now, it's an angle, so it shouldn't have units. So when we look at this, we notice that we have 2 pi, and t is in seconds, period is in seconds, so those units cancel out. Then we have 2 pi distance in meters, wavelength in meters. Those units cancel out, so this becomes unitless the way we would want it to be. Now, what exactly does all of this mean? Well, let's look at this wave that's traveling, and we want to compare how a point right here at the origin travels with respect to a point somewhere else along the wave. So let's pinpoint 2 of those points and check out their phase angle. So here we have the point at the origin. So when I'm going to look at the phase angle, 2 pi over t, 2 pi over period times time minus 2 pi over lambda times x, I notice that the x, which is a displacement from equilibrium, is actually 0 because it is at the origin. That means that we're left with 2 pi over the period times t, or 2 pi ft. So the point at the origin has a phase angle 2 pi f times t. Now what about a point farther along? At this point, we still have 2 pi over period times t minus 2 pi over lambda times x, but that x is no longer 0. So if I write 2 pi over period as 2 pi ft, then write lambda as v over frequency, remember that velocity is lambda times f, then I get 2 pi ft minus 2 pi v over frequency times x. And if I factor out 2 pi f, then I am left with t minus x over v. So this is the amount of time it takes for the first impulse of the wave to make it to that point. So this is what where the velocity comes in, how fast the string is moving, so that this point gets that first impulse and starts moving up and down. So now let's look at the speed of sound. And the sound propagates differently in different media. It largely depends on the density of the medium, because sound needs a medium through which to travel. So it counts on particles bouncing off one another so that they create this condensation and rarefaction, where the particles come closer together, bump, and transmit that energy, or move apart, and then they experience that condensation again. So for an ideal gas, the speed of sound is given by square root of gamma kt over m. Let's recall that we learned about the RMS speed of a gas in a cubical box, and we said that that was equal to 3 kt divided by m. This is very similar to that, except gamma is actually the adiabatic constant that we dealt with before in thermodynamics, where gamma was Cp over Cv, the specific heat capacity at constant pressure divided by the specific heat capacity at constant volume. So that's where this gamma comes from. K here is Boltzmann's constant. It is not the K that we had here for the wave number. So that's the Stefan-Boltzmann constant. T is temperature measured in Kelvin, and m is the mass of the molecular mass of the gas. Now for sound in liquid, V is the square root of the adiabatic bulk modulus divided by the density of the liquid. So we're using the adiabatic bulk modulus because as sound propagates through media, there is not really any heat transfer through the medium. There is a little bit of temperature difference between condensation and rarefaction, but not sufficient to actually cause any significant temperature changes or heat. And then for the speed of sound in a solid slender bar, V is going to be square root of Young's modulus divided by the density of the metal. So these speeds get progressively faster because the particles get progressively closer together, and they can the particles can meet one another a lot faster to transmit the sound through the material.